Till now we have seen that magnetic field outside this toroid as well as inside a point of this toroid both are 0. This is 0 and this is 0. Inside, because there is no current enclosed by this loop, and outside because current coming out is equal to current going inside. So these current will exactly cancel each other. That's why there is no magnetic field outside the toroid as well. Now let us see the third case. Third case is inside the toroid. So this is the outer radius of the toroid and this is the inner radius of the toroid. So previously we were either outside of the toroid or we were inside the toroid, but this time what is happening, we are somewhere in between this toroid. So this is inner radius, this is outer radius, this time we are somewhere in between this toroid. Now let us see what will happen in this case. Radius in this case is R2, outside radius is R3, inside radius was R1, this time radius is R2. Now let us see what will happen in this case. Let the magnetic field inside the solenoid be B. We now consider the magnetic field S. Once again we apply this Ampere's circuital law. So we know this L is equal to 2 pi R. What is R here? R here. R is the average radius for the solenoid. So we know that solenoid has two radius, one is outer radius, one is this inner radius. So this is Ri inside Ri, this is outer radius. So R is average radius, R is equal to Ri plus Ro by 2. So average radius of the toroid. So this R is the average radius. So we know that magnetic field is B. So this is written wrongly, solenoid, this is toroid. We can also say it solenoid because it is also a solenoid with circular, with that is folded in a circle. So this is also a solenoid that is folded in a circle. So we can also say this is a solenoid, but better word is toroid. So what we find, this L is 2 pi R, where R is the average radius of this toroid. Now the current enclosed IE. So what is the current enclosed by this loop? So let us see what is the current enclosed in this case. So let us move to the figure and let us see what is the current enclosed. So if you see in this circle, there is only one current enclosed, this is not enclosed. This current coming out of the plane of paper is not enclosed, only one type of current is enclosed, which is going inside the plane of paper. So both the currents will not cancel out. Now we know the current enclosed is not 0 in this case, that means magnetic field will also not be 0. Let us apply the Ampere's circuital law. So current IE is simply current I into number of turns in the coil, because we know current is multiplied by number of turns for taking the enclosed current. This time this current is not cancelled because there are n loops, total number of loops n. Again see here, it is capital N, not the number of turns per unit length. Now let us apply the Ampere's circuital law. So magnetic field B into L is 2 pi R, where R is the average radius, which is equal to mu naught Ni, total current enclosed, mu naught into IE is Ni. So this is Ampere's circuital law. So solving this, what we get? We get this B is equal to mu naught Ni upon 2 pi r. So this is the result for when we are between the two coils of the toroid. So these are two coils, we are somewhere between the two coils. Then what is the magnetic field? Mu naught Ni upon 2 pi r. So we shall now compare the two results. So this time we are going to compare the two results, one for the toroid, another one for the solenoid. First thing, when we saw the case of solenoid, this is solenoid, this is toroid. So for toroid, what we see that there is no magnetic field here, there is no magnetic field here, only magnetic field is inside this region. That means inner radius and outer radius, only here we have some kind of magnetic field. Okay. Similarly, in solenoid, we have magnetic field only inside the solenoid, outside the field was 0. Now we are comparing the results of the solenoid and the toroid. We re-express this equation to make comparison easier with the solenoid. So let R be the average radius of the toroid. So this R is the average radius of the toroid. So we know what is this R. R is the average radius of the toroid. Now we know N upon H is equal to N, the number of turns per unit length. So now when we took solenoid, this length was H. This length was H. And this length has been turned into circle. So H is equal to 2 pi r. H is equal to 2 pi r because this H length has been turned into circumference of this solenoid. So H is equal to 2 pi r. So what we have? Capital N is equal to small n into H, and we have H is equal to 2 pi r, N into 2 pi r. So this is number of turns and number of turns per unit length. So if N is the number of turns per unit length, then total number of turns are equal to this total length. Suppose if we open this coil, then total length is H, and this H is equal to 2 pi r. So what we have, total number of turns is equal to 2 pi r into small n, that means average perimeter of the toroid. So what is the perimeter? Perimeter is 2 pi r, and r is the average radius, so we have called this average perimeter of the toroid, and n is the number of turns per unit length. Now let us put these value into this equation. So let us put this value of N. So what we get? B is equal to mu naught, value of N is 2 pi r, N and I and 2 pi r. So this 2 pi r and 2 pi r gets cancelled. So what is remaining? B is equal to mu naught N I. So this is the same result as for the solenoid. This is the same result for the solenoid. Why it is same as solenoid? Because a toroid is also a solenoid. What we have done? We have just folded it like a circle. This is also a solenoid which is folded like a circle. So this is also a solenoid. So magnetic field in both the cases is same. In an ideal toroid, the coils are circular. In reality, the turns are toroidal coil, form a helix. So what they are trying to say, ideally this coil should be a circle. Okay, this should be a circle coiling, but you know that coiling cannot be circle. Coiling is always a helix. Ideally coiling should be a circle, but this coiling is not a circle but a helix. So because of that, there is always some magnetic field outside the toroid. So what we have seen here, outside the magnetic field was 0, but in reality we have assumed that this is a circle, but in reality nothing can be circle, this is only a helix. Because of the helix there is some magnetic field outside the toroid as well.